Okay. Nope, that's not what I wanted. Where's the buzz? Okay. Nope. Okay, there's no buzz now. Be there in just a second. What the fuck? Okay. Hey, Roots. Hey, there, Katie. Yeah, he's been tormenting me by doing stuff about black holes. Um, it feels personal, even though I know it's probably not. Um, he's had to get himself involved with physics. Uh, I understand the camera's probably not great. I have to use my phone because I can't find the right cable for my camera. And I had to set everything up again. It's been a while. Let me know if you can't hear me at all.
Hello, and welcome to the mrgirl podcast.
Oh, I gotta say, I sided with the physicist leaving during this. I already seen or listened to this at least. I listened to it at work. Well, I had it open. I was watching it too. I had one of Mr. Girl's fans was gonna argue with me about this, but then they decided not to do that. So I wasn't gonna pressure them to do so. The fact that anybody's here after how many times I stalled on this, I was trying. I just couldn't get the stream set up. I appreciate you being here.
We have Paul Sutter. You're a
Oh yeah. Also, I'm gonna try to when I agree with the physicist, I'm gonna see how well I can try to explain what's going on, put it into layman's terms, see if I can maybe post some stuff up on the internet to help translate some of the physics stuff.
physicist,
We'll see. I can't remember. Other than I fully agreed with him leaving when he did. I thought he was actually pretty patient.
professor.
Occasionally. It's my day job.
How would you describe yourself?
I would describe myself as a scientist and a science communicator.
Okay, and you have a podcast.
I do have a podcast called Ask a Spaceman.
And I saw that you. So I asked you on to talk about whether the universe is a black hole, and you did an episode on this very topic.
I did. So you're just gonna play back that entire episode for this interview. This will be great. I'll go get a snack.
And we're done.
And we're done.
Okay. Do you have any questions for me?
I do like that the physicist is using like an RGB mic. I don't know why that's funny to me, but I think that's very funny.
Before we start talking about this, or is there like a meta discussion we should have about?
There's not
about
a meta
talking?
discussion. Are you worried that the universe is a black hole, or are you excited by the prospects of the universe being a black hole?
I don't think I feel great about it.
Not so great. Okay, well,
No.
this interview is going to be great because
I'm very convinced that it is.
Okay, you are super into the black hole is the universe idea.
Well, if your question is like, is my interest emotional rather than theoretical? No. But if you're asking me just like point blank, how do I feel about it? I gotta say, it's not the most thrilling prospect.
But you're still attracted to it.
Well, I'm not attracted to it. I just think it's true.
Okay.
Okay. I'm not attracted to, thinking this is gray, but it looks gray to me.
Looks gray to you.
But I've noticed that physicists are like, I have found it hard to talk about this with physicists. So like I'll have all kinds of different experts on my podcast. Psychologists, epidemiologists, which is whatever, and people feel kind of free to kind of just like throw ideas around.
Oh yeah, is the sound okay? Can you hear me okay? If anybody could comment on that, that would be a big relief to me.
But I found that this cosmology and black holes, maybe because it attracts a lot of crazy people. I don't know what it is, but it feels like. Also, I think maybe because the field doesn't exactly know what's going on, it just seems like kind of like a touchy subject in a strange way. Is there any validity to this observation, or have you noticed this?
Well, physicists are touchy people in general. We don't like it when people call our ideas into question, even when we admit that they're wrong. So there's that whole thing.
Okay.
But in general, there's a lot we do know about the universe, and then there's a lot we don't know about the universe. And it can be very easy to mix up the parts we don't know with the parts we do know, and to take the parts of cosmology that are open questions, that are active research questions right now, the things we are trying to understand about the universe. And it's very easy to take those bits and import them and cross-pollinate them with the things that we do understand after doing physical cosmology.
I just want to point out that there's two different things that we call black holes. I probably talked about this before, but over here, so I'm going to go over it again. There is a predicted black hole, like a theoretical black hole. And then there's this thing that we observe that we call a black hole, but we can't say that what we're seeing, this event that we're witnessing, is the same as like a theoretical black hole, which is what we predicted we would find that acts similar to this black body object that we see, which is just why we call it a black hole. But there's no way to prove that this is the thing that we've mathematically predicted existed. By nature of it, if it was the thing, we wouldn't be able to prove it anyway.
For a century. And yeah, I get a lot of people, a lot of questions, a lot of genuine interest, and a lot of people who think they have their own ideas about how the universe works. And, honestly, in cosmology, just like all of science, you are welcome to have the wildest idea you could possibly imagine. Wild ideas are always welcome, but they always have to meet the evidence. And yes, there are many, many things, and we can talk about those many things in cosmology that we do not understand. But then there's a very, very long list of evidence for things we do understand, and we have to separate that wheat from the chaff in order to make progress in understanding.
Okay. All right, how do you want to do this? Do you want to say why you think the universe isn't a black hole?
Show. Hello? No one's here. You're fine. The other dogs are barking. Okay.
Or should we maybe a brief overview?
So we have theoretical idea of what it is, but we can't confirm what we observe maps onto it. So there has been a predicted mathematical black hole. So Albert Einstein, general relativity predicted the existence of black holes. He initially doubted their physical reality, later acknowledged their existence. His theory continues to be used to study them. That's the basic, like, Google AI explanation of it. So he predicted them, and then we have some math that represents what they ought to be and what would be required for them to form. However, when we observe these, I just say events because we can see activity. You can't see a black hole. That's what makes it a black hole. But we can see things happening around this area, and it's close enough to what we would expect this thing to be, but we don't have any proof of it. Like, we can't confirm that this is what it is. It's also, like, the theoretical black holes, by some metrics and some understandings of the math, would be impossible. for a couple of different reasons. So it's always a little bit sketchy when we talk about them. We can say some things about like the event horizon is something we can observe. We can talk about that pretty well. But to make a claim like the universe is a black hole is such a weird thing to say because we don't really know what we're talking about when we say it. Relax, pup. You're okay.
Of the standard model.
That's a great place to start. Yeah.
So, sorry, go ahead.
Oh, no.
And a lot of people don't like to acknowledge that, even though it's fundamentally true that we can't know.
So about 100 years ago, we discovered two things simultaneously. One was based on observations and one was based on theory. One theory, the theory
I forgot. I didn't know he was going to go right into that.
Was the development of Einstein's general theory of relativity. This is our modern understanding of gravity. And in that theory, we discovered that the universe's natural state is to be either expanding or contracting, that a static, fixed universe that exists throughout all eternity without changing on the very largest scales is actually a very unnatural place for the universe to be. That is not its natural equilibrium. It's naturally dynamic. It's naturally evolving. So we discovered that on the theory side, and then simultaneously, unbeknownst to the observers who are making these measurements, we discovered that the universe is expanding, that galaxies on average are moving away from the Milky Way galaxy, and that the further out you go in space, the faster that velocity is. The easiest, most simplest, most parsimonious way to explain that raw observation is that we live in an expanding universe. And hey, we have a new theory of gravity that explains, that says that the universe should be dynamic. It should be moving at very, very large scales. So these coincided right next to each other in the 1910s and 1920s.
And if you're unfamiliar with this stuff, what he's saying is not really debated. It's none of this is really contested.
And then since then, we've built a massive accumulation of evidence for what became known as the Big Bang Theory, which is we live in an expanding universe. Our universe is getting bigger and bigger every single day. That means in the past it was smaller. That means in the past it was more dense. That means in the past it had a higher temperature. And from that basic statement, from the statement that the universe was smaller in the past, which is a wild, radical, revolutionary idea, you can make all sorts of cool predictions. And these predictions have been borne out by observations. Like one of the keystone things, one of the measurements that I personally worked on is something called the cosmic microwave background. This is leftover light.
Happy to have you, buddy. Also, still what he's saying, not contested. The cosmic background radiation. There's even a map of it. You can Google it, and you can see like a map of the visible universe, and there will be like a green tint. Cosmic background radiation. Give me 1 minute. Background radiation. Images. Here is a link to the Wikipedia of the cosmic background radiation. This is which is sort of a byproduct that there's cosmic background radiation. Yeah, it's accepted science. Sure, that's a totally fine way to put it too. I personally have a gripe with the Big Bang Theory. I'm more of I think the universe always existed, but I believe allows for some expansions, and like multiple bangs to occur within an ever-existing universe. Oh, yeah, I got you, Katie. 1 minute. It's on Mr. Girl's Substack, which is annoying, because I thought it'd be like on his Rumble or something too, but it's not. It's just on the Substack, I think. Oh, yeah, the cosmic background radiation. I mean, we can detect it. Let me see. let's see. Okay. Let's see. Yeah, let's see. None of them really have any steam. Sure. You're correct, Roots. The mapping of it is they have measured tiny variations and almost constant microvariation with all sorts of stars and galaxies stuff. Sure, I would say that's it's a vague enough model to give people the idea. 100%. Pure chill.
When our universe cooled from a
think so, yeah.
plasma state, a hot, dense plasma state, and cooled to a neutral state. This happened when our universe was about 380,000 years old, released this absolute flood of radiation that persists to the present day. And this radiation, if you put
Yeah, we got it. But I appreciate you.
on microwave goggles, it completely swallows up the entire sky. We're we're in this bath of fossil radiation that we can observe. And it has the properties that we predict it should have. And there is no other theory of the evolution of the universe that successfully predicts the existence of the cosmic microwave background and matches its known properties. The only theory that remains is the Big Bang Theory, that our universe is getting bigger every day. And that is the main story. That is the central story of modern physical cosmology. Everything else flows and follows from that statement.
And we don't exactly know why, but we've ascribed this expansion to dark energy, right? Which is
it's actually a step before that. Like right now, the expansion of the universe is accelerating. And we discovered that.
I think they're going to go over it, but when they say dark energy, what they mean is we don't know. The same thing if you ever hear dark matter, it just means we don't know what it is. We can't explain this, so we're going to use a filler word to say that something's there, even though we have no idea if something's there or not. Same thing with dark energy.
This in the late 1990s. We call that acceleration dark energy. We have no idea what dark energy is. We have no idea why the expansion of the universe is accelerating.
Right
so the initial expansion would be the propulsive force from the Big Bang, and then the additional acceleration we're calling dark energy.
Yes, I don't want to use the propulsive, like that term propulsive force, because it's very easy to get, because Big Bang is such an alluring term. It's such an evocative term. It also gives a very, very incorrect mental picture of what's happening in the early universe. The universe.
Dark matter is the difference between the expected rotation speeds versus the mass of the galaxies. We can't explain why. And so we say there must be something there. But it could also be the case that when we look at things on the scale of galaxies, that the laws of physics don't operate in the same way in which they do on smaller scales. Like, we don't really know what's going on there. We seem to find that when we get into like particle physics, things don't behave in a way that aligns with the classic model. It seems like at different scales, different things apply. And dark matter and dark energy are just kind of ways to say we don't understand why these very large things aren't complying with our models that we have that work at this scale. And I just don't like that we use words for them, because it makes it sound like they have some idea of what's going on with it when we don't.
naturally wants to expand. It is its natural state. If you take a bunch of stuff.
But there is a great paper out there which says the gravitational influence in the light comes from huge galaxies. That is gravitational influence. If you want to link me that paper, I'll take a look at it. That might make them seem like they're moving faster and slower due to gravity. It does get kind of wonky when we're using light as our way to determine how these things are moving when there is massive pockets of gravity. So it's tough to say. It's tough to say what's really going on there. I think a lot of the stuff, like when we talk about dark matter and dark energy, or things like WIMPs, weakly massive interacting particles, are just ways for physicists to keep trying to sound like they have a handle on more things than they do.
And you put it inside.
But part of the reason why I think that happens is because we haven't made a ton of progress in physics before the LHC, at least. We've made some, I would say, some pretty significant finds there, but since like the 50s. So I think it's important to make it sound like there's a better grasp on things than we used to have, because it's such a slow-moving field. From like, I would say from like the 1910s and 1950s, we were finding a lot of stuff. And then it just, progress just sort of slammed on the brakes. Arguing is kind of a difficult way to noodle reality out. I agree. I used to have many hour-long conversations with a friend of mine about physics for a couple of years. It was just, I think conversation is a much better way. A conversation rooted in curiosity is a really good way to go about it, I think.
Side of a universe and you hit the go button, it is naturally going to expand or contract. That is what is going to happen. And whether it's expanding or contracting depends on how much stuff there is in the universe. If the density of matter in the universe is above a certain threshold, the universe will be collapsing. If it's below a threshold, the universe is expanding. The amount of stuff in the universe is below that threshold. We find ourselves in an expanding universe. We do not know where the universe comes from. We do not know how the universe started. We don't even know if that question even makes sense. That is beyond known physics. The story of the Big Bang is the story of the evolution of the universe since its very earliest days. And that story is one of expansion. And then on top of that.
Hey, Victor. Kind of watch this physicist get upset with Mr. Girl and leave. And talk about why I think it was pretty okay for him to leave. Where I think a lot of people that leave Mr. Girl's podcast are leaving from a pretty weak position. I think that the physicist is the most understandable of anybody's that I've seen.
That, on top of that natural inclination to expand, to be dynamic, we find that expansion accelerating. We do not understand the cause of that acceleration, but we have a really cool name for it, which is dark energy.
Okay.
I do appreciate that he admits that.
All right.
So flatly.
How are you most comfortable?
When this guy says physics, he means theoreticals, because that's what he learned when he got his master's, the physicist. Some of it's theory, some stuff we know.
Going forward, talking about whether the universe is a black hole, do you want to talk
Physics is a hard science, but there's also theoretical physics as well.
about why you think it looks like it isn't? Or should I talk about why I think it is?
Let's start with you. Let's hear it.
All right.
Like I said, wild ideas are always open. We just have to meet them with the evidence.
Okay.
I was just talking about dark energy. They'd understand. Because nobody understands that. Understanding what is causing the universe to expand wouldn't make you a professional. It would make you the top dog among all physicists.
For an observer in a
Hey,
black...
Froggy Style, thank you very much for the gifted membership. We went to the Clark Cunt. Couldn't have gone to a better person.
I'll just walk you through kind of like my train of thought, and then you tell me when I say something that you think is wrong or right.
Or I'll let you finish. I'll let you do the whole spiel because, you know, there are parts that may connect.
Well, I think
with each
if
other.
no, I think if you have a fundamental disagreement with part of it, we should address it.
Okay, fine.
Okay. So for an observer inside of a black hole, all geodesics lead to the singularity. Is that true?
You may continue.
He does do a good Vsauce. Physics theories aren't in contrast to biblical facts.
Okay, so if you're in a black hole, you shine
I like that.
a laser pointer. You're shining it at the singularity, no matter what direction you shine it in.
Is your name Genova, like Sephiroth's mom? Biblical facts are history, but history is written by the victors.
Okay. All other objects in a black hole, therefore, are on...
Wait, what?
You're shining it at the singularity, no matter what direction you shine it in. Okay. All other objects in a black hole,
Genoa.
therefore,
Gotcha.
are on... fall on a geodesic between the observer and the singularity.
Not necessarily, because you can have parallel geodesics. You can have parallel paths that are both headed towards the singular.
Just to make things easier for everybody to understand, I'm just going to Google definitions of words instead of trying to explain them from my head. A lot of this stuff's pretty old to me, so I have sometimes rusty, but sometimes maybe just not your very easily translatable understandings of some things. Geodesic is the shortest path between 2 points on a curved surface, analogous to a straight line on a flat surface. So when they say that, that's what they're talking about. He's agreeing now, but they never get past the first point.
Singularity, that doesn't necessarily mean one is in front of the other.
Well, if the observer, if any line drawn from you, let's say you're in a black hole, any line you draw from you has to go from you to the singularity. So anything else you see is in between you and the singularity.
The math inside of a black hole gets really, really strange and very counterintuitive. And statements you make that might make sense outside of a black hole do not necessarily make sense inside of a black hole.
This is true.
Is there something about this that doesn't make sense?
So it is possible, like for, say, for you, if you fall into a black hole and you cross the event horizon, you can still see light from the outside universe, because light can still fall in along with you. It can still fall in after you. You can look around.
I don't think that's true, but I don't think light can come in after you. I think it would come in at the same time.
So the physicist is right. I think that mrgirl gets hung up on some of the weird ways that we describe time when it has to do with black holes. Most persons are pretentious and rich city slickers. I don't know how much most of them are,
due to infinite time dilation.
So there is no infinite time dilation inside of a black hole. The infinite time dilation does not happen at an event horizon. It actually only happens. It doesn't even happen at a singularity. This is a very common misconception about the structure of black holes and what happens at event horizons. When you free fall, which is the simplest case you can imagine, if you're taking a freely falling particle and you allow it to cross through an event horizon of a black hole, and say, let's say you are that particle. You let go, you turn off all rockets, all propulsion, simplest case possible, and you allow yourself to freely fall into a black hole. You are going to experience time dilation. That is a real thing because of the massive gravity in gravitational density of the black hole. But that time dilation does not go up to infinity. In fact, at the event horizon, it's roughly a factor of 2. So the outside universe is going at about double the speed that you would normally observe it as if you were not outside of if you were outside of a black hole.
So you're saying if I throw my watch into a black hole at the event horizon, it will only slow down by a factor of 2?
We have to separate, and this fundamental disagreement about
from my observer perspective.
From your perspective, so the example I gave was you freely falling into the black hole, and then what you would say about the outside universe.
Right.
What the outside universe has to say about you is different. So, and this.
I just spent 4 hours in a conversation with my super artificial intelligence. Constant real-time clarity sharing, not in conflict. I think part of the problem that Mr. Girl has with physics is he's mostly talking to ChatGPT about it. Although I will say what the professor's saying is not about time dilation, is not. It is contested. It isn't to say that it's wrong. I probably lean a bit more towards what he's saying. We have math that suggests that it approaches infinity, but there's nothing that suggests that it ever reaches infinity. There's just no way to. There's no way to justify an infinite time dilation. Hand to chest micro expression, by the way.
This fundamental disagreement actually bedeviled even Einstein himself. He did not know what to do with the nature of the event horizon about this fundamental disagreement between observers. It would take all the way until the 1950s and 60s before we began to understand what happens. And what happens is there is a divergence in perspectives.
Tools, not toys.
You falling into a black hole, you do not experience infinite time dilation.
Infinities are a great example of broken physics. That's not true. There are infinities, and there are an infinite number of infinities. Just even in mathematics, just broadly, like obviously, like there's an infinite number of numbers, not whole numbers, but like between 1.1 and 1.2. There's infinite number of 1 point. You can go on forever. That's the simplest way that I can explain it. Theoretical physics, it's not a hard science.
You only experience time dilation like up to roughly a factor of 2. If you, let's say I'm the one falling into the black hole, will sacrifice me for this experiment.
There are infinite.
If I'm the one falling into a black hole, and you watch me, you never see me cross the event horizon. From your external perspective, I get stuck on the horizon. I slow down and I slow down and I slow down. The light emitted by me gets more and more redshifted, and I look frozen and infinitely redshifted on the surface of the black hole. You never get to see me pass through.
Yeah.
My perspective looking out at you is very different.
Yeah.
As I fall in, you seem to speed up by roughly a factor of 2, and then I cross the event horizon. Light from you still follows me in. Light still punches through the event horizon of the black hole, can still reach me.
That's correct.
And I still see you waving goodbye, even though you never see me fall in. And I know this sounds contradictory, but this is the only way to resolve what happens at the event horizon.
What do you mean it's the only way to resolve it?
As in the presence of the
Do you want to elaborate on that, Victor?
The event horizon appears in the mathematics of general relativity as what's called a singularity. It looks like there's this infinite divergence of
Singulator.
like particle behavior, of redshifting, of time dilation. But then you realize that this is a matter of perspective, that from outside observers, they do see this infinite divergence and this infinite slowdown. And
infinity is a misleading concept. Mathematicians make absurd claims about it. And in physics, it's never real. It's at best shorthand for a really huge quantity. Kind of. There are examples where infinity is the correct variable. I was working in Planck lengths to Proxima Centauri actually earlier today. How cool! I just mean the idea of infinity is that nothing can be understood because it goes on forever, but it's not possible that everything can be discovered. I don't think that there's just because there's an infinity just doesn't mean that we can't understand it. Like there's bigger and smaller infinities. Like I said, you can come up with infinity number of numbers between 1.1 and 1.2. The same you can do with 4.1 and 4.2. So there's larger and smaller infinities, for sure. That's the easiest way to explain it. But and that can be understood perfectly well.
Infinite redshift of anything that falls into a black hole. But when you follow the actual trajectory of a particle or a test object freely falling into a black hole, moving towards a black hole, then it gets a completely different picture.
Okay, maybe we need to get into what like a definition of simultaneity. But so, say I start a stopwatch on my watch, and then you jump into the black hole.
Mm-hmm.
At some point, my stopwatch says it's been 10 million years, and you're showing me your watch, and I see that or even if you weren't showing it to me, if I was calculating what time it is on your watch, I would calculate it's been 5 minutes.
Is
that accurate?
So
from my perspective outside the event horizon.
So the calculations you make are going to be different. So the calculations you make of my watch from your...
I gotta go back a little bit because what was just said is an important part, I think. A lot of what the professor says just seems like mumbo jumbo to me, to be honest. It's not for sure that there's bigger and smaller infinities. Well, do you contest? I'll make it even easier that there's an infinite number of numbers between 1 and 2, and that there's an infinite amount of numbers that can be made between 4 and 5. If so, then there's got to be bigger and smaller infinities, at least in terms of mathematics.
So the calculations you make of my watch from your perspective,
yeah, that's what I'm talking about,
are different than your calculations of my watch from my perspective.
Yeah, I think they're in agreement here.
I think that we'll just talking about my perspective.
Okay. From your perspective, your calculations of are exactly right. Let's say you wait outside that black hole for 10 million years. You're a very patient guy.
It's been 5 seconds for you, right?
And you see me only like 5 seconds. And that is something you can observe because the light coming off of me is still coming off of me, and you could read the watch on my wrist.
Sure, but
yeah, you're correct, leader. If we're talking about dividing things, then yeah, I would say the Planck length, from everything that we understand, is as small as it gets.
It's not just a optical illusion. In my observer perspective, it literally, your watch is only 5 seconds have elapsed on your watch.
Exactly, and I appear like frozen in time, essentially.
Okay. One of the postulates of relativity is that my frame is valid, that this is actually happening.
Yes.
Okay.
For you.
Yeah, so I think I think maybe I just don't agree with what you're saying.
Sure,
Because if
Roots.
it's been 5
I don't
seconds on
disagree
your
with that.
watch and 10 million years on mine, you're saying
But they're still different sizes.
for you, if you have 5 seconds on your watch, you're saying if you calculated what my watch said at that moment with the same perfect knowledge of relativity, you would get that it's only been 10 seconds for me.
Yeah. We are going to disagree, and this is
Wait, where did they disagree?
You're saying for you, if you have 5 seconds on your watch, you're saying if you calculated what my watch said at that moment with the same perfect knowledge of relativity, you would get that it's only been 10 seconds for me.
Yeah. We are going to disagree, and this is the fundamental tenet of relativity, is that measurements of time and space, measurements of length and duration, depend on the observer, depend on their perspective. Different people, different observers are always going to disagree about how large objects are and how long durations are, and
But this is
mathematics.
This is different from just a disagreement. This is a simultaneity disagreement.
But there is no guarantee of simultaneity in relativity.
This is when, what does your watch say when my watch says X, right?
From my perspective or your perspective, like the whole point of relativity is that we always have to pay attention to the observer's frame of reference. We always...
I brought up Planck's in little respect for the celestial contribution. Those aren't different sizes. The numbers are in one set are bigger than the numbers because you can pair them off. I'm not sure I understand what you mean by that, Roots. Like, if 4 is bigger than 2, then the infinities between 4 and 5 would be larger numbers than the infinities between 1 and 2. Everything they put out is subjective in their own words.
All measurements of time and space are relative to a particular observer.
I don't know what you're trying to get at with that. That's so to me, I'm taking it.
The observer's frame of reference.
Everything everybody says is subjective in their own words.
We always, all measurements of time and space are relative to a particular observer.
Yeah.
Mm-hmm. That's true. But
according to my watch, according to me, I die in a matter of seconds. I cross the event horizon in a finite amount of time, and then I die. And I hit the singularity.
But at the event horizon.
At the event horizon, at the moment I cross the event horizon.
What mine says, for me, mine says 10 million years, yours says 5 seconds. And then you're saying for you, when yours says 5 seconds, mine only says 10 seconds.
Yes. Welcome to relativity. It's a pain. It's a headache.
I don't know if I don't think I agree with that. But let's disregard that, because I don't think if the universe is a black hole, I don't think there's anything outside of it falling in anyway. So it's not really material to my argument here.
No, I'd say relativity
the
matters
point we were
a lot.
at was if you're in a black hole and everything else is also in a black hole, then anything you see must be between you and the singularity.
But that is not correct, because I can see other observers, or I can see other objects in parallel to me, and I can see objects behind me. But I do know that all of my future directions do lead to the singularity.
How can you see something behind you?
Because light can still move inside of a black hole, and light can still move. It can still catch up to me inside of a black hole. So I can turn around, I can be inside of a black hole, and I can still turn around and see the outside universe.
Let's say there isn't an outside universe, so we can.
Okay, that's a very common technique to simplify calculations. We're going to put a black hole inside of a vacuum. We'll have perfectly empty flat space, and then we'll have a black hole in the middle of it.
Okay, so you see a baseball. If you were to shine your laser pointer on the baseball, you would be shining it along a geodesic that leads between you and the singularity. Is that true?
Potentially, I'd have to do the detailed math in front of me, but we can continue.
Okay, it's not that there's a singularity in front of you and that you are. It's not like everything will end up there. It's that you can't actually even perceive a direction that is not towards the singularity. Everything goes towards the singularity. There is no longer such a thing as a direction that is not towards the singularity.
I don't know if I can use that kind of language inside of a black hole, because I do know where the singularity is. I can perceive it, and
I don't think that's true.
Okay, so this is the second time that I've said something very plain from the mathematics of special relativity, and you've disagreed with it. So,
well, how would you perceive where the singularity is if you're inside of a black hole?
There's a difference between the number of numbers in a set and the size of numbers in this set. There's nothing infinite about any numbers between 1 and 2, and infinity only comes up with the number of numbers. Sure, I don't disagree. Surely there can be a degree of paths. Once you'd be inside of a black hole, it would be a totally different frame of reference than outside of it. I understand why Mr. Girl is saying what he's saying, but everything's being affected by the gravity the exact same way. So, how you would observe things directionally wouldn't be any different than you would observe things. You wouldn't be looking behind you by looking straight ahead. We can go deeper into it another time when we're not watching something else.
The singularity is the place where there's no light emanating. So if you would imagine nothing can, once you're inside the black hole, the singularity from our outside perspective is a point of infinite density.
In the center.
In the center of the black hole.
Yeah.
Once you're inside the black hole, there's actually extreme gravitational tidal forces that bend the path of light. And the point-like singularity actually gets stretched out, and it looks more like a disk. And then the closer and closer you get to the singularity, it actually stretches out and it looks like this, like you're landing on a gigantic black planet. And then once you reach the singularity is the point where the black planet has like reached all the way up to be perfectly flat, and it stretches from horizon to horizon. And the reason for this is that light that is within the black hole, light that has fallen in from the rest of the universe. I know in our example, we put the black hole inside of an empty universe, but let's imagine we illuminate it. Light is coming in from the outside, and light, once it enters the black hole, also all
How can we talk about black holes and other astrological phenomena when all we have are pictures and haven't ran scientific experiments? The professor is right to talk about. So what he's talking about are the black holes we have on paper that and then relaying it to say as if the things that we're observing that we call black holes are the same thing. This is super common. And for the most part, to have conversations about black holes, this is just sort of an unfortunate misstep that we have to let go. This is how everybody talks about black holes. We talk about them as if they're the same. We're just sort of like giving this unjustified thing up. Don't bring your light. But let's see here. You really can't run experiments on black holes, but we can work out the mathematics of how things would go. And so, whatever Mr. Grill is saying, if he's engaging with the idea of a black hole, he has to engage in the same framework, which means he's still subject to the same mathematics that the professors confide to in this conversation. So, like, what they're talking about is really just like this theoretical mathematical black hole. That's the only like arena in which they can butt heads about black holes in, not necessarily the things that we're seeing.
All the light is going to end up at the singularity along with you. There is light that is ahead of you that is reaching the singularity. There is light that is catching up from behind you that is reaching the singularity. There is light that is coming from the left, coming from the right. Everything's headed to the singularity. So I can look around.
Yeah.
And I can...
Assuming you could actually move.
I can attach an accelerometer to myself so I can measure my relative orientation inside of the black hole. I can look around. I can see the outside light. It gets squeezed into a donut shape around me because of the extreme gravitational forces and the tidal forces that are doing really, really weird stuff to space around me. And then the singularity itself even appears distorted.
But without an outside light.
The math is all the battle when it comes to black holes. It's the only thing we can observe. Or it's the only thing that we can engage with this idea about black holes with, because of the nature of what the thing that we look at and call a black hole is. That's a very funny place to pause.
Okay, if everything's just black,
Well, yeah, everything's black. There's light in the black hole, but you wouldn't know where the singularity was.
You can identify the location of a singularity inside of a black hole.
If you're in it.
If you are in it, yes.
How?
So the light that has fallen in, because the singularity is still a location in space. Even when you're inside of a black hole, the singularity is at a particular location in space. It has a coordinate.
I don't think that's true.
I think I understand why Mr. Grill doesn't think that's true. If you're outside of a black hole, the singularity of the black hole doesn't seem to have a location, but it's more or less its destination mark is one of time only. But once you're inside of a black hole, there is still some space to traverse before you reach the singularity. But from outside of the black hole, it doesn't make any sense to say that.
Once you're inside it, I don't think that you would be able to identify where a physical location. Because
I think that if you engage with a lot of stuff about black holes, it's very easy to make that mistake. A while ago, I did a stream where there was a black hole expert who talked to Neil deGrasse Tyson, and she talked about how a black hole singularity is it's not a location in space, but rather a location in time, like at the event horizon. But once you're in the black hole, that would change.
It would be in every direction. I don't think that. So,
You have the event horizon, you have the black hole, and then you have like the singularity at the very center of it. So once you're past the event horizon, you've entered the black hole. There is still space between. Mr. Girl's right. All the light is going to the singularity, so none of it is going to your eyes. It's tough to say if it would like literally go to your eyes. I don't know if that's something that we could know, but just that's weird to talk about. Um, for a couple of reasons. Um, I don't know if light's behaving like a particle or a wave inside of a black hole, and also it's the way that your retina interacts with light. So the singularity appears in every direction. Once you're in the singularity, yeah, but not necessarily once you're in the black hole.
Gravitational lensing changes the apparent location of an object, right? And size, angular size. So if I'm shining my laser pointer around, say I'm shining it at the moon.
Also, hi, Sawyer.
Or and next to the moon, near the moon, but the moon suddenly increases in mass. A huge amount. My laser pointer will eventually be shining at the moon, even if it's at like an off angle, because the curvature will increase, and the moon's location in my view will effectively increase. Its size will increase. Is that true?
Yes. I can use gravitational lensing and the bending of space to distort images.
Okay. And so that off angle. So let's say right now, the moon has mass, right? So right now, let's say if I shine it a millimeter off.
Good timing, Sawyer. We just got to the moon analogy.
So it would, if the moon were massless, it would miss. But because the moon has mass and there's curvature, now this geodesic actually does lead to the moon. Is that logical?
Say that again.
So the moon has mass. And if the moon didn't have mass, let's say there's some angle, some infinitesimally small angle, where if I shine my laser pointer 1 millimeter to the left of the moon, if the moon had no mass, my laser would miss. But if the moon has mass, my laser will hit it.
Yeah.
It creates a little gravity well that a little bit amount of curvature, and if we increase that amount of curvature, then that off angle also increases. That if the moon were massless, I would miss, but because it has mass, there's curvature, and my laser photons will curve in and hit it.
The laser that it's not going to hit. And that's because if you imagine taking the moon, or sorry, like a circle, an imaginary circle the size of the moon, and you point a laser pointer, let's see if what I just said is true, and you point a laser pointer right at the very edge of that, or just past it, like you draw that imaginary circle, it's a half a degree across, and you point your laser pointer just to the right of that circle. Then you replace it with the moon, and now it is bending space. That laser pointer doesn't hit the moon. Instead, it grazes by the surface of the moon, because I haven't changed the spatial extent of the moon. I've replaced that circle on the sky with a different object. But now, because of the mass, when the laser goes by the moon, when it grazes the surface of the moon, that's when it gets deflected. And so it will end up at a trajectory pointing slightly behind the moon instead of going in a straight line.
Are you saying that there's no alteration to the photon's path until it passes an object? Wouldn't there still be curvature between me and the moon? anyway?
There is curvature, but
So there is some amount of curvature. I mean, all we need is that there's any amount.
there is curvature.
Okay.
But in terms
Oh shit!
of deflection of angles,
I haven't.
I'm trying my best to imagine a scenario, and I could be wrong about this, where like I'm looking at the moon and say I'm pointing a
Oh, maybe. Send a link.
laser like just inside, or I'm pointing at a particular crater, and then I increase the mass of the moon, and I don't think angles are deflected in that way.
The question is a little frame blending, because you would no longer... You're going to perceive the path of the laser as a straight line. So you wouldn't see it curve in. You would just think the edge of the moon was there now. If it were much, much more massive. And so,
I know when light is bent because it follows a locally straight path, but it can curve. Like if I would just sprinkle, say, dust along the path, and so I could illuminate the scatterings of the laser beam.
I'm not sure about the moon thing. I'd have to draw it out, I think. I might be inclined to agree with Mr. Girl about the laser, but I think I'd have to draw it out.
I would see it curve for sure.
You would see it curve if you could see the whole light path.
how?
You'd have to zoom out a lot.
Back, the reflection path back would be along the same curved path.
If it's scattering light, like if I'm scattering dust along.
He's talking about a reflection path back, which would be different, which he's correct there. But if you were able to zoom out and somehow still see that little bit of light, you'd see it curve.
Along the path of the laser, then that...
You can, but wait till the video's finished up, and then I'll
scattering goes off in all directions, so everyone gets to see the path, whether you're right here lined up with the laser or not.
If right. So but from your perspective, if you're just looking down, you would. So for you think you're looking at it in a straight line at the moon. Let's say I'm watching you do this experiment from way above, then I would see a curved path.
But I would see a curved path too, because imagine that straight line, like you're holding the laser right at your eye, and let's say it goes straight, but then it starts to curve to the left a little, just in this random example. Okay. Because the scattering of the magic pixie dust is scattering that light in all directions, I see that beam of light going off to the left because some of its light is getting scattered back to my direction.
I'm not sure if I agree with that, but do we agree?
So that's the fourth time I have to stop here. So that's the fourth time that I've explained something from basic physics, and you've said you don't disagree with it. You have every right to disagree. But really? It is disingenuous to bring an expert onto a show and then
this is what I was talking about earlier, where nobody knows the answers to these things.
See, because I don't have the math. I'm not working out that math. I'm gonna agree with the physicist on that. Although I'd have to draw it out for me to know for myself. For sure. Let's see. Notes on disagreements. Oh, I didn't see this before. I'm gonna I'll have you call in just a second. Sawyer. What? There we go. Oh, that cuts me off. I want to just put this in text to speech, so I don't have to read it all.
At around 1530, Paul and I disagreed about what an observer falling into a black hole would experience in terms of time dilation. Paul proposed a 2x limit on how quickly clocks would run in this observer's frame.
I like this this voice for this. Okay, cool. It did switch. Perfect.
Paul proposed a 2x limit on how quickly clocks would run in this observer's frame. But this limit only applies in a very specific scenario, and I believe we got our wires crossed here.
I think so too.
Paul proposed a 2x limit on how quickly clocks would run in this observer's frame. But this limit... Paul proposed a 2x limit on how quickly clocks would run in this observer's frame. But this limit only applies in a very specific scenario, and I believe we got our wires crossed here. In the standard framework of general relativity, it's important to distinguish between what is occurring in an observer's frame versus what they are physically perceiving. For example, there may be a galaxy merger occurring right now that we will not perceive for millions of years.
Sure.
When Paul referenced a 2x limit on how quickly external clocks would run in that infalling observer's frame, he was referring to the maximum speed of pulses the observer would physically receive from a clock placed at infinity, in flat Minkowski spacetime. For this limit to apply, the observer also has to have fallen from rest at infinity, and it only applies to photons arriving from directly behind the observer. If the clock is placed at any other angle or the observer starts their fall from less than infinity, the observer will receive signals arbitrarily fast. The 2x limit in this very specific scenario is the result of a competing redshift and blue shift. The velocity of the infalling observer relative to the clock approaches light speed, causing a Doppler redshift. The frequency of pulses they receive slows down because the observer is nearly outrunning them. At the same time, the observer is approaching a black hole, so gravitational time dilation increases toward infinity, causing a gravitational blue shift. The frequency of received light pulses increases. Both effects mediate each other such that the maximum rate of pulses received is 2 ticks per second on the infalling observer's clock. If the observer starts their fall from less than infinite distance, or if the clock is closer than infinite distance, or if the observer accelerates or decelerates, the 2x balance will be thrown off. For any angle other than directly behind the observer, the blue shift increases without bound and the frequency of received pulses will approach infinity. This means that the 2x limit is actually a blue shift floor, not a ceiling. Even if you were to fly a spaceship at top speed into a black hole, photons arriving directly behind would end up at a 2x frequency compared to your watch. All other angles would arbitrarily increase toward infinity. As I mentioned, the frequency of pulses received by the...
I don't think that's true. Oh wait, I'm sorry. It says the photons. Never mind. I don't disagree with that then.
As I mentioned, the frequency of pulses received by the observer is different from what is currently happening in the observer's frame, in the standard framework. As an infalling observer approaches an event horizon, all clocks in the universe will indeed tick arbitrarily fast in the observer's frame, regardless of what signals they receive. Our disagreement about whether time dilation can be interpreted equally and oppositely from either perspective seems to have arisen from this confusion about whether we were talking about what is happening in an observer frame versus what those observers would physically perceive in terms of received light signals. This whole argument is a bit confusing because I usually argue against the standard definition of what is happening and actually prefer the observer's received signals as the definition of reality. But since the argument is about how time dilation works in the framework of general relativity, I want to be careful and clear about differentiating these concepts. I also don't believe that black holes can physically exist as fully formed structures identical to the mathematical objects, because they would take infinite time to form. This was Einstein's view. Can you physically see the curve of a light path originating from your location? Paul hypothesized that if you shined a laser near a massive object, you could use dust to scatter the light rays and thus visually reveal space-time curvature. This would not work because the scattered rays would follow the same curvature back to your eye, appearing to follow straight lines from your perspective. You would need to move to a different vantage point to see the curved path of the laser through the dust. Can you detect the location of a singularity if you're in a black hole? No, and for the same reason you can't visually see the laser curve from its origin point.
Ah, we're so close. In a black hole, there's no other location from which you can see curvature towards the singularity. You are always at the origin. I disagree with the last part. Playboy Cardi. I'm pretty sure I know who that is. Oh, yeah, I hate it. I hate it so much. I thought that's what it was. That coworker listened to it while I was getting a ride from them, and it was terrible. I hate it so much. I'll try to work that out for myself. The laser at the moon, but I'm gonna take the physicist's word for it right now. I'll have to draw it out. I'm having a hard time just visualizing in my head. He's a woman beating drug addict. He's awesome. His music fucking sucks. The coworker that played it for me, like all the music he likes, I think it's just like terrible. I don't like mumble rap at all, and his is a little less mumbly, I think, but I didn't like it at all. I'm pretty picky when it comes to rap. I wish they would have engaged more about like the zoomed out observer instead of just, it's a laser. You don't need to scatter dust. You can just see a laser. But yeah, I think that once you're inside of a black hole, you have a different frame than. I think that mrgirl thinks the way that we would calculate, or the way that we would see things, based on the properties of a black hole from the outside, is the same as how we would, the same frame we would see things through the inside of a black hole, and it would be different. The only thing that gets tricky here is the word see, because like you wouldn't see anything. It would be very unlikely that you would see anything, because I don't think it would be very likely that any photons would enter your retinas. That makes the whole argument kind of silly. It's just Gen Z music. I don't have to get used to it. I'm just going to listen to other music. I hate it. I hate it a lot. It's so terrible to me. And like the voices and like the production on it, I just don't like. Some of it had good beats, but like, oh man, the Condensed matter physics is not condensed milk, is that? Okay. Yeah, the idea of seeing in a black hole is silly. I feel like we have to talk about it. You have to grant a different kind of lens in which like sight works like magic. The reality is we don't know anything in space is composed of, so we can't make assumptions with clarity. Quantum dynamics matter. Well, like this isn't really a conversation about what a black hole is made of. Like it's not made of anything. It's just an event. I would refer to it as an event. I think that's a more accurate way to represent it than calling it a thing. Sorry, my black hole suddenly had a gravity well infinite, and an asteroid was deposited in a whirlpool of visualization. I hate it when that happens. What time is it? Okay. I'm glad this worked. I gotta find a cable so I can use my regular camera again. Oh wait, I gotta let Sawyer in. Did he join? He didn't join. I sent him an invite. Are you still there, Sawyer? Unkind interlocutor. It's a thing. Victor is just plays. I think that's it for tonight. Then I didn't have Victor here. What the fuck was I gonna say? I'm trying to stream. I'd like to stream more. Just haven't had my meds in a long time, and that makes it a lot harder to do anything constructive. But I'm getting to the point where it's been quite a while, so it's not as bad as it was. But even when I stream on work days, I won't be able to stream until like 1 a.m., which sucks, or like at like noon, which is garbage time to do it. Well, even before that. Stream when you have coffee. It's not about me being tired. But I drink a lot of, I consume a lot of caffeine. It's just not the same. There's a very cool amount of people to be here, though. I appreciate it. I kind of want. There's some other stuff. Oh, wait, I can talk for like a little bit. I invited you to the. Okay, you're there. All right.
Wait, hello?
Hello.
Hey,
Hey, give me 1 second.
I had to close your stream, so I can't see what you're doing anymore.
I just put in Discord on the screen, just so there's like your thing is flashing when you talk. Okay.
I just want to talk about the moon, and like I was pretty surprised you were disagreeing that you would see the singularity in every direction inside an event horizon.
No, I didn't say that you would.
Yeah, I think that you would.
Wait. Hold on. You said inside the event horizon, not inside of the black hole. These are different things.
Within the Schwarzschild radius of the singularity.
If you're in... Hang on, I think if you're in the singularity, you wouldn't see...
Wait, did you follow the part about, like, if the if the moon increased significantly in mass, it would appear much larger. Do you agree with that? Like the apparent angular size of the moon would increase with its mass.
Yes, of course. It would curve. It would space would curve more.
Yeah. Okay. So if the moon's mass increases a lot, it would fill up the whole sky, and then eventually, if it's heavy enough, it appears. No matter where you look, you see the moon.
Well, you wouldn't see it behind you.
You would. It would fill every direction.
Well, if it increased enough, then it would collapse into a black hole.
Yeah, exactly. So if you're in a black hole, you see it in every direction. The singularity. I mean, it just appears as darkness on your horizon.
We're just so really when we're saying it's increasing in mass, we're just saying that it's increasing in density. Like it's only getting denser though, right? Its size isn't changing, correct?
Mm-hmm.
It would just be pulling in more light because of the spatial distortion from the gravity, right? Space-time curvature increase. Yeah.
That's what gravity is.
I'm making sure we're on the same page. That's all.
Yeah.
Sometimes I talk to people and they say things. It's just important to make sure that we're both saying the same thing. That's all.
Yeah, I'm just saying, like, it's not like a thing that happens as like after the like it's just that literally is just like, you know, what gravity is. Increased spatial curvature.
Yeah, I don't think that I still don't think you would see it behind you.
So you think it would be limited to 180 degrees?
Well, wait a minute. So here's the problem that I have. Just like when they were talking about seeing inside the black hole, we kind of have to grant seeing this magical quality all of a sudden in order to see. Right?
Because the photons are falling into the singularity?
Like, you need photons to hit your retina in order to see. And like you would have to be blocking the path of the photon, your eyes would, in order for you to see anything.
Okay.
So in this scenario, we're granting sight like this magical quality where like photons don't have to enter your eyes to see something, right?
Well, it's a bit confusing, but do you want to change the analogy to not seeing the moon, but like they were talking about in the conversation, shooting a laser at the moon?
Sure, but sorry, just one moment. Genoa, thank you very much for subscribing. I appreciate it. Oh, and Victor as well, thank you very much. Sorry. Yeah, let's do the moon laser.
Okay. So the laser doesn't have to make it back to you in this case.
Yeah, I feel like that part made the conversation less productive. I don't know why the moon I don't know why the laser had to come back to you.
Well, the reason he was saying that, he was saying the deaths because he was arguing that you could see the curvature of the laser, which I don't think you could.
You would if you were zoomed out.
If you were looking at it from an off angle, but not if the laser was like originating from your eyeball. Yeah,
because that's how light is already traveling.
Yeah.
That's just how things look.
Like if you, the analogy that I use to understand this was like, if you fired a laser down a tube and there's two options. It was either a tube of length like L, or it was a tube in two segments with like a 45-degree mirror. You wouldn't be able to tell which option it was just by firing the laser, and then like you wouldn't be able to tell if there was a mirror there. But if you looked at it from above, it'd be very obvious. I don't know if that makes sense.
I think I understand what you're saying. I think would this work for you? I kind of like the idea of the tube. What if there was a instead of just using a laser, you could just say it doesn't have to be light, right? You could just send out matter in a perfectly straight line to meet that.
Yeah.
And if you went in a perfectly straight line off from where the moon should be, would it collide? Yeah, from your frame of reference, if you're going off, I don't see how it shouldn't change then. You should still be off.
Well, what I'm saying is that the area, yeah, so like you would see the moon as getting larger, essentially.
If you
That
increase
the area,
mass,
if you increase the mass of the moon. But again, if we're not using sight, it's the angle at which you could shoot a laser towards the moon would increase as the mass of the moon increased.
yeah, eventually at a certain point, the light would have to get pulled in. Right, well, yeah, it would have to at a certain point. I guess I would just say if you just set out like a detection. Let's say you just sent out a piece of metal that's designed to detect when it comes in contact with something. If you went off a millimeter from the side of the moon, if it increased in mass, eventually it would curve into it.
Yeah.
It would have to.
And the same is true for a photon.
But Mr. Girl didn't say anything about increasing the mass. He just said if it has mass.
Well, he's saying because the moon has mass currently, there's some angle that you could fire a laser so that somebody who existed in a universe without general relativity would see it as missing the moon. But from your perspective, there's some slight extra angular size that the moon has because of the gravity created by it.
I think I understand what you're saying. So you're saying turn the mass of the moon off, and then shine a laser, and then if you turn it back on, then laser with it. Yeah, okay. I just think he did a poor job of explaining that, or maybe the conversation made it difficult to understand that.
I think the physicist understood what he was saying, but I don't think that was the reason they disagreed, is because they weren't on the same page.
Wait, Mr. Grove did say increase mass?
Well, the point of the analogy is to demonstrate that as something increases in mass, so too does its angular size. Apparent angular size.
If what you and I just discussed is what he's saying, then he was not incorrect.
Well, do you agree with this, that the mass of something affects its apparent angular size?
Yeah.
Okay, so this is the reason that when you're within the event horizon, you see the singularity not as a point in space, but as surrounding you in every direction. No matter where you look, you see the singularity.
I think that. So this is the problem, though. Like a black hole. Like if you're in the singularity, I'd say sure, probably.
Within the Schwarzschild radius of the singularity.
Yeah, but they were just saying as you approach the singularity in the black hole. And then also the weird thing
the radius of the event horizon is defined as light cannot escape the singularity. the escape velocity from the singularity is greater than the speed of light, which means that any direction that you fire a laser inside an event horizon, it ends up at the singularity.
Yeah, it ends up there, but I still think once you're inside of it, you have a different frame. Well, kind of.
Well, if you're...
Like I said, I feel like you probably can't see anything unless you're like in light, and then you can just see that light. The seeing is a weird way to put it.
Well, yeah. I mean, I agree. It's kind of confusing, like how you can see stuff.
Yeah. Do you agree? In order to discuss this, we have to grant sight this magical property where it just like sight works. Like,
well, I don't know that you do because I think
you'd have to be like in light in order to see the light. You wouldn't be able to see light that's in front of you because it hasn't touched your retina yet.
Well, you see, you would still see light emanating, like if we're looking at the light from a distant galaxy.
We're seeing light that is touching our retinas, though.
Yeah, so it has a path from the galaxy to us.
If you enter the event horizon and then light enters right after you, there's a gap there, and that light's not touching your retina. Once you're inside the black hole, there's a chance that light hits your retina, but unless it does, you're not going to see it. Like, it could be directly in front of you, and unless it touches your retina, you're not going to see it, which makes the conversation pretty weird.
Yeah, it's kind of a different...
Which is why I said, like, in order to talk about, like, what you'd see, we have to kind of grant sight this, like, property, which, like, sight is something that extends from the eye at faster than light in order to work.
Yeah, well, we can just use the analogy of shooting a laser. So if you are within the event horizon and you shoot a laser, no matter what direction you shoot the laser, it ends up at the singularity.
Well, eventually, but while you're in it, it's still not like so if I'm in the event horizon and I'm headed towards the singularity, so I'm spinning around it, and I point a laser behind me, the light's going to end up following me, but I can still look behind me if I'm able to see somehow. I'm still going to see that behind me. I'm not going to see that light where I am or in front of me. But if all I could see, if I could see the singularity in every direction, then no matter where I would look, I would also just see the light that the laser that I just shined.
Yeah, so do you agree that the singularity appears to be in every direction? I think the way that Mr. Girl thinks that sight works in a black hole is that like if you have two galaxies falling towards a singularity, one of them's us and the other one is closer to the singularity than us. If there's a photon emitted from the galaxy closer to the singularity, then we would fall into the photon.
But it would just end up like matching up.
Like if the photon's emitted from the galaxy opposite the direction the galaxy is falling, it has a lower effective velocity towards the singularity, and so we eventually collide with the photon, even though everything is moving towards the singularity.
But once you're at the event horizon, from your frame, you still have a more or less like you have a velocity that is separate. That is like anything that enters the event horizon. It doesn't all just like meet up at the same time. There's still they still have a velocity. It doesn't like equalize out everything that's ever entered it. Isn't like meeting up until the point of the singularity.
Yeah, but I'm saying from any observer's perspective, distant galaxies are going to be closer to the singularity than them, because the singularity is essentially the edges of the observable universe. And so if we use like Andromeda as an example, Andromeda emits a photon. The photon, if it's emitted towards us, it's effectively in the opposite direction of the singularity. Then we collide with the photon as we all move towards the singularity at the end of time.
That would be true even if there wasn't a singularity, though.
Well, if space was flat, it would just be the path of the photon just hits us.
Okay, and then what's the difference?
Well, I was just trying to resolve this question of how do you see in a black hole if the singularity pulls everything towards it. And I think Mr. Girl's answer to this is that you essentially fall into the light.
How do you gain on the light then? Velocity would increase relative to the distance.
Well,
to
the light has
singularity, no?
Yeah, but the velocity of the photon is the speed of light, is c.
Mm-hmm.
And the difference between us and Andromeda is not greater than c, otherwise we wouldn't be able to see it. So if Andromeda is moving towards the singularity with velocity 5, and we're moving towards the singularity with velocity 3, and the photon has velocity 3 opposite the direction of Andromeda, then we collide with the photon.
Rather than the photon colliding into us, or?
Well, I don't know. It's the same.
Okay, I wasn't sure how you're trying to say those.
I don't know. It's a bit confusing. I'm a little confused talking about it, but I just wanted
use a
to
visual aid to try to imagine what you're saying. That's why I was saying earlier I'd have to draw it out. Some of the things are kind of hard to visualize. You don't see the light because the singularity has maximum angular radius from everywhere inside the black hole, meaning it's all going to the singularity in both your eyes. I understand the idea, Roots. I understand why Mr. Girl is saying what he's saying. I understand this idea, but I don't agree with it.
Well, how do you not agree that the singularity is in every direction?
How do I not agree?
Like, just taking the moon analogy, you just increase the mass of the moon. It appears larger and larger. Eventually, it fills up the entire, every direction, right?
Well, it would appear larger and larger until it collapses.
Well, if you just ignore the fact that let's just say it doesn't collapse.
No, I think that there's no, I just don't think. I think at a certain point it doesn't work anymore. It has to collapse. I would say up until the point of reaching the density required for a black hole.
What's the limit to the angular size of the moon from your perspective? If you're floating in space.
Well, I just said the limit would be up to the point to where it would have to collapse into a black hole.
So how big is the moon in your perspective at that point? From like an observer perspective. Like what? I mean, at some point, no matter where you turn, you're just going to see the moon, right?
I'm trying to visualize right now. So Yeah, I still think that at a certain point, it just eliminates the ability to see it. How does light? It is, yeah, at a certain point, I guess that you wouldn't, seeing it wouldn't even make any sense because there would be no light to see. Uh,
Well, yeah,
because they'd all be moving
the
along curved
it would
paths
become
to it.
yeah, it'd become like red, and then eventually it would just appear as
Yeah, so I can understand what
darkness.
you're saying from being a person on Earth looking up at the moon, which is why I said too. I think that Mr. Girl has an idea of what the inside of a black hole is like, based on how it would mathematically work out if you're looking at the black hole from the outside. But once you're inside of it, I don't think that that's the same thing anymore.
Well, from the outside, it's just like everything falling towards a point in space.
If it was the case that the moon would behave this way, then when you looked at a black hole, if you could look at a black hole, then it should be doing the same thing. But it doesn't. There's a limit to it.
But because we're not close enough to it, so the curvature caused by the black hole is not sufficient from our perspective to make it appear to be infinitely large. I mean, it's the same. The gravity from a black hole with 15 times the mass of our sun is the same as the gravity from a star with 15 times the mass of our sun. But if you're close enough to it, if you're within the event horizon, then the effects are sufficient that no matter where you look, you see the black hole.
I don't think so. Even in the event horizon,
Or you would see darkness.
You can see light moving around. Now, you'd probably just see darkness because you'd have no chance of light entering your retina. But if you're in the event horizon, like we can see the event horizon, and there is light moving around the event horizon. So if you're in it,
there's no event. There's no actual event horizons in our universe.
There's no start. There's no definite start and stop to it. Like we can't define these like borders of it. But we have observed event horizons of a black hole.
Well, we've observed things that are approaching, but an event horizon cannot form in finite time. Like, it takes infinite time for an event horizon to form, by definition, because time dilation at the event horizon is infinite.
So this obviously isn't true because it exists, but mathematically, yeah, that's what we expect. But observation says otherwise.
Well, the observing something that's infinitely close to an event horizon is effectively, or
it's not infinitely. It's not defined.
What?
Well, the event horizon, like I said, there's no defined borders of where exactly it starts and stops.
Well, I'm defining an event horizon as the boundary at which light cannot escape the singularity.
Sure.
Okay, so that an event horizon cannot form in finite time from any outside observer perspective. So effectively, there's no true event horizons in the observable universe.
Except for our observation of event horizons would contradict that.
Well, for observational purposes, it's the same. If you have something that's nearly an event horizon or something that is an event horizon, it's identical. I mean, for practical purposes, like if you get something close enough to an event horizon, the light is so redshifted you can't detect it anyway. So it's like the same as no light being emitted from it.
Do you disagree that we have photos of the event horizon of a black hole?
I disagree that it's a true theoretical event horizon.
Okay, so this is like the thing I was saying earlier, where we have the theoretical black holes, and then we have these things that we're observing that we just sort of relay our idea of what a theoretical black hole is onto it.
Yeah, we just call it a black hole because it's the same for observational purposes.
It
But it's not.
seems like it is, at least. We don't know that this is what it actually is.
Well, mathematically, it can't be a true event horizon because it would require
Mathematically, a black hole can't exist.
Yeah.
But we have these things that we refer to as black holes that clearly exist, that do have event horizons, like what we're calling event horizons, which does seem to be light not being able to escape the gravitational pull of what's happening in this event.
Yeah, I agree with you.
It's tough.
Saying that a black hole exists or can exist just means that.
Well, the theoretical black hole, at least.
Yeah, it just means that the sum of forces in the system, gravity is dominant over everything. So it's the indefinite collapse of, like when Oppenheimer was doing that thing in the movie, and they published a paper showing that black holes
I didn't see it.
can exist or whatever. Like this is what they're saying. Okay, well,
I have no frame of reference, unfortunately.
You need to choose a different reference frame. It's just that if you get a massive enough like star and it collapses rapidly enough, it will overcome any sort of electromagnetic force that wants to maintain a size in the object. But the effects of general relativity, an event horizon cannot form in finite time.
I understand that, which leads to a disconnect between our observations and the theoretical black holes.
Well, it's not a disconnect because, like, the things we're observing are just like 99% black holes, and I think it is. A lot of people like don't really realize that that's what's happening, but
they don't realize what is happening.
That every picture we take of a black hole, everything we call a black hole is really just something very close to a black hole.
Yeah,
if you're defining black holes theoretically as the boundary at which light cannot, or a boundary at which light cannot escape.
I try to make sure that I explain that every time I talk about the subject.
Okay. Why did we talk about this?
I don't know. I got lost in our conversation. Just going from one thing to one thing.
Yeah.
Well, I'm gonna. Wait, no, I do agree with the moon laser thing. Yeah, we already resolved that.
Okay, so basically, I just think that Mr. Girl was completely right in the conversation with the physicist. Is there any point at which you think the physicist was right and Mr. Girl was wrong?
I think it's more sketchy watching it through the second time. It's harder to tell. Well, yeah, I still think that if you're inside of the singularity,
well, you can't be inside of a singularity because the singularity occupies no space.
Well, past the event horizon, or sorry, inside a black hole. My bad, I misspoke.
Okay.
Yeah, that was wrong. Yeah, well, if you're inside a black hole, I think that if sight works in a fantastical way where you don't need light to hit your retina, you can see, and like you can look in 360 degrees still, while moving towards the singularity. Do that, or you just see nothing at all because you're not having light hit your retina.
Well, light does hit your retina. So
why? There's no guarantee of that.
I feel like I need to like draw something out, but I don't think we can really do that right now.
I agree. Do you want to? I guess that it seems like a fair point to say. Do you want to try to come up with some diagrams and reconvene at a later time?
Yeah.
Because I
don't
think
know.
even when I read physics books, I draw out diagrams when I'm reading things, because it's some of these things are so hard to visualize without something concrete to like anchor you there. At least for me, I usually have to draw diagrams.
Yeah. Yeah, a diagram would probably be helpful.
Hmm.
And I do have to go pretty soon anyway. But okay.
Okay, and I'll try to draw something to represent what's happening inside of there and why I don't think. I think it's crazy that you think that like with a high degree of certainty that you think that light would be hitting your retina while you're inside of a black hole prior to post event horizon pre singularity.
At a certain distance from you, the light can't reach
But
you, and this is the
it would
this is the
have to be entering with you at the same time, and that's all you
no
would be
no
able
no.
to see is that light, really.
We're already in the event horizon, and
Watch
so
it.
the edges of the observable universe, where essentially we see distant galaxies moving away from us faster than the speed of light due to dark energy. This is when the light can't reach you anymore, and over time, this boundary gets closer to us as we, in the Max Carson model, as we all get closer to the singularity. But if something is close enough to you, your velocities towards the singularity are similar. So imagine like us and okay, so imagine I'm in a car and you're in a car, both traveling faster than the speed of light down
Same direction?
a road. Yeah, yeah. And you're ahead of me. And you shine a flashlight towards me. I'm gonna see that flashlight
Yeah,
because
I'm gonna
I'll
go
run
past
into
that light and you'll run into it. Yeah, yeah, sure.
yeah. So that's what's happening with Andromeda, for instance.
Wait,
That's why we can.
so you think that you're falling in towards the singularity faster than the speed of light?
Uh, well,
It doesn't
I think
really matter
so.
what the speed is, because even if you're moving in towards the singularity at faster than the speed of light, so is the light. So it really, like,
Yeah,
unless it
yeah, yeah.
enters at
So
the
we
same
are
time as
because the
you,
light. Yeah, to be within an event horizon, you have to be.
sure, but that means everything else that enters before and after is still going to be moving at the same speed anyways. So you're still not having light hit your retina. Everything's still following the same rules that you are in terms of moving.
Yeah, but
Unless we want to grant light a special property where it can move
well,
faster
you can't see
than
anything
another
that
body.
enter. You can't
That's
see
what it's.
anything that enters after you. But for something that enters before you, it's just like the analogy with the cars. It's like we're all moving towards the singularity, but the light is effectively
No, but
moving slower towards the singularity if it's emitted in your direction, from your perspective.
it's still going to be falling towards the singularity at faster. It's going to reach the singularity before me. It's not going to reach me because I'm still behind it. That light is now also moving towards the singularity as soon as it's emitted. So it's not going. There's no way for the model in which you're describing allows for something to go faster than other things inside of the black hole, or pre or post event horizon. That doesn't make any sense to me. I think everything has to be moving
You
with
think
the same
everything has
velocity.
the same? Well, that doesn't make sense because something
If you're
closer to the singularity would have more velocity towards
then it
it.
would never reach me, or then I would never reach it. And if it entered before me, it would never reach me because I would always be outpacing it. Everything ahead of me will always be outpacing me, and I will be outpacing everything that's behind me. And when I say ahead and behind, I mean in my path towards reaching the singularity and spaghettification. So there's like no way for light to ever reach my retina.
If the light's emitted towards you,
So okay,
it will never escape the singularity, but you catch up to the light.
here's the problem. Can you see me?
I don't
Or
think so.
okay. By the way, the Schwarzschild radius of the universe is the actual radius of the universe. Yeah, correct. So,
The what?
kind of. I was reading a chat. So by the way, the Schwarzschild radius of the universe is the actual radius of the universe. So we're in a black hole, strange as it sounds. If that's how you want to define it, I don't think that's the case.
I don't really know what that means.
So the Schwarzschild radius is the amount of matter that has to exist within.
Oh wait, yeah, okay.
So like if you have X amount of matter and like Y amount of space, this is what will cause like the amount of gravity to exceed to the point to where it's just like collapsing in on itself and creating a singularity.
Yeah, but that doesn't really, it's not really relevant, right?
Seems like if the light hits your eyes, then it wasn't on a geodesic that ends in the singularity. Yeah, that's like there's I think that it's not well. Yeah, the thing that makes it impossible here is that if I'm moving faster than light towards the singularity, and there's also light that's moving faster than light, are we saying that something? So, oh wait. I'm sorry. I want to get back to what you said. If the light is emitted behind, so you have point A, and there's light being emitted behind it, and I'm at point B, moving towards where that happened. As soon as that light's emitted, it's still going towards the singularity. It's not coming at me at the speed of light. It starts. It comes out, and it tries to go the speed of light, but it just ends up going towards the singularity. And it's ahead of me. So therefore,
perspective,
perspective doesn't matter there. What's happening is that light can't go backwards. It
can't go backwards, but it effectively slows down going towards the singularity because it now has an additional.
It's not being propelled out of a laser pointer. It's just sort of bleeding out of the laser pointer towards the singularity at that point. And if it's ahead of me, it's just at the point at which, like the end of as soon as that light comes to come out, it's gonna go in that direction with everything else. I'm not gonna meet it. It's not gonna meet me. It's still ahead of me, so I'll never catch up to it. Still.
Well, I can't really follow what you're saying because I think that.
We'll reconvene with diagrams.
Okay.
I'm using my phone as a webcam right now because I cannot for the life of me find USB-C to USB 3 for my camera. I don't know what the hell happened to it. So I've just kind of like really crunched down in this tiny little box that just works for this camera. But I could explain this pretty well, I think, with a diagram. But I can understand why it's hard to visualize otherwise.
Well, I feel like I have a pretty good visualization of.
Right, but we don't agree.
Why?
If we had visualization, I think it would be easier for us to understand why we're disagreeing if we had some kind of diagram. You go, okay, right here, this is the part that's incorrect, and we could sort of like point to it.
Yeah, probably.
But I appreciate the conversation.
Yeah. Okay. Me too.
Do you have any final thoughts before I wrap up the stream?
Well, I don't know. I kind of forget why I felt the need to call in, except for the moon thing. But yeah, I don't think so.
Okay. You feel free to reach out to me anytime.
What were they had 4 things they disagreed about. I can't remember what the other ones were.
Time dilation.
Oh, yeah. But you agree that time dilation at the event horizon is not 2, but infinity.
I have to say that mathematically, it just keeps increasing. But we don't know. I have a hard time with that level of increase. I'm not sure where I land on that. I've never been sure where I land on that. I think that when we get to certain things, break our conventional understanding of physics, and I think that that's like a black hole is going to be one of those things that breaks our like conventions where like we can use math to like accurately determine like how much is actually being dilated by time. So I don't accept that it just like indefinitely approaches infinity.
Well, I just think that's what an event horizon is. Like, if you don't have infinite time dilation, then you don't have an event horizon.
Why?
Because if it was finite time dilation, then light could escape.
Well, no, that's not true. You're only saying that. Well, you're saying that because, in contrast to the gravity, I'm saying that once gravity is amped up to the point of a black hole, I don't think that the same metrics apply to time dilation. I think time dilation works just fine when we're using non-black hole levels of gravity. But once we get into that level of gravity, just our traditional understanding of time dilation probably doesn't apply anymore. So the gravity is still present to not let the light escape, but I don't think that the light or that the time dilation that would follow if we use our standard model for how we would map out time dilation v gravity is going to continue to stay the same. Similarly to how like classical physics works just fine, but then once we get down to particle physics, it sort of falls apart. I just think that once we enter a certain level of extreme, we can't just rely on the same math to map things out correctly. And especially since the implications of infinite time dilation just sort of defy our understanding of the universe, and like the idea that a black hole exists would defy our understanding of what time is. It just seems like something has to be, our expectations are off based on the mathematics that we're using, because they probably don't apply in this situation. Too many other things break.
Well, an event horizon means there's a causal disconnect between something within an event horizon and something without an event horizon, or outside an event horizon. Right? Like, because of the fact that light and information travels at the speed of light. So you can't have an event that happens inside an event horizon affecting outside an event horizon. And so at the exact distance from a singularity that is an event horizon, light is frozen, essentially. Which means time dilation is infinite. Time effectively stops, because nothing can... And there's no reason why general relativity can't follow here. Like, because there are no event horizons in our universe. It's just something gets very close to an event horizon. But it requires infinite time for an event horizon to form. I mean, I agree it's like confusing to think about this and try to talk about it on the fly, but I don't think there's a problem with Einstein's math here. And Einstein's math is that time dilation goes to infinity.
It approaches. It doesn't get to infinity. It approaches infinity.
Well, at an event horizon, it would be infinite. There's a divide by 0 in there.
Yeah, I do think that is incorrect. But just reach out to me. We'll reconvene and flesh this out in a better way. Do you know how to use like a screen share for like diagrams?
Yeah.
Okay,
I think I
cool.
used Discord whiteboard once.
Okay, that can work too. All right, I appreciate the conversation.
Okay. All right, later, man.
Peace out. All right. Well, thanks for being here. Uh, and also, I want to say thanks again to Victor, Genoa, and Froggy Style for the gift of membership. Oh, sorry, Froggy Style for the gift of memberships, and Victor and Genoa for subscribing. I appreciate it a whole bunch. Sometimes I do physics. There's some people I haven't seen here before. I don't always do physics. Mr. Gurley triggers me about physics, so it ropes me into it. But I'd like to stream again soon. I'm not going to make any promises on when, just because I've been bad at that lately since I've moved. Because I don't have my meds, and it makes it harder to do. But if you're in the Discord, if you're not, I do put out a tag for the Discord when I do. Oh my god. I did use the copy button, didn't I? I didn't. Oh my god. Oops, wrong thing. There we go. That should fix it. There we go. You can join if you'd like. And anybody who joins, I'll give the stream